Hello, my dear students of Standard 11. Welcome back to your Chemistry 1 class. In previous classes, we are talking about the arrangement of electrons in different orbitals for atoms. Here, we have learned about the three principles by following which the electrons are arranged in different orbitals. Today, we will discuss about the deviation of writing electronic configuration. That means we will discuss about some atoms where the rules are not followed for writing electronic configuration. Normally, most of the atoms follow these principles for writing electronic configuration, but there are few atoms which do not follow the rules. So, today our topic is deviation of electronic configuration. Now, deviation of electronic configuration for Pauli's exclusion principle. All you have remembered about Pauli's exclusion principle. The principle is the four quantum numbers of any two electrons of an atom will never be identical. At least one value must be different. Pauli's exclusion principle is followed by all the atoms. There is no atom which don't follow Pauli's exclusion principle. But if any atom has only one electron, then Pauli's exclusion principle cannot be explained by using the example of this atom. For example, hydrogen. Hydrogen, it has only one electron. So, Pauli's exclusion principle cannot be explained by using hydrogen. Its electronic configuration is 1s1. So, hydrogen has only one electron. So, Pauli's exclusion principle cannot be explained by using the example of hydrogen. Other all atoms follow Pauli's exclusion principle. Now, the second rule, that is Hund's rule, deviation of Hund's rule. You have remembered what is Hund's rule. Hund's rule is applicable for degenerate orbitals. That means when electrons go to different degenerate orbitals, then before making pair, at first the electrons go in every degenerate orbitals in same direction, and after fulfilling the degenerate orbitals by one electron, the electrons will make pair in degenerate orbitals. Hund's rule is also followed by every element. But you know, there are some atoms for which the electrons will not go to degenerate orbitals. Hydrogen, it has one electron. Helium, it has two electrons. So, the electronic configuration 1s2. In this way, lithium, beryllium, 2s1, 2s2. So, degenerate orbitals are not needed to arrange the electrons for these elements. So, look. Hund's rule is also supported by all the atoms, but the atoms whose electrons are not arranged in any degenerate orbitals like hydrogen, helium, lithium, beryllium, and also boron. Boron, it has 5 electrons, so one electron it goes to 2px orbital, but only one electron. So, also by using boron, we cannot explain Hund's rule. Here, the electronic configuration of beryllium is 1s2, 2s2. There is no degenerate orbital, so we will not explain Hund's rule by using beryllium. In the same way, boron, it has one electron in degenerate orbital 2px, but only one electron, so Hund's rule cannot be explained by using boron also. Now, deviation of electronic configuration from Outbound principle. You know, Outbound principle is the main basis of electronic configuration, and there are some atoms which don't follow Outbound principle. Why these atoms don't follow Outbound principle? The electronic configuration of almost all elements can be confirmed by Outbound principle, but there are some deviations noticed for a little amount of elements. To measure reasons behind these deviations are more stability of half-filled and full-filled orbitals, and second one is very small difference of energy between NF and N plus 1 d orbitals. For these two reasons, very few elements don't follow Outbound principle, or the electronic configuration is deviated from the general rule. Now at first we will explain about more stability of half-filled and full-filled orbitals. Degenerate orbitals, PDF, gain more stability when they are exactly half-filled or full-filled. For example, p orbital, it has total 6 electron holding capacity. So P3 it is half-filled and P6 it is full-filled. So NP3, NP6, ND5, ND10, NF7 and NF14. These configurations are more stable than other. For this reason, the configuration N-1D5 NS1 becomes more stable than N-1D4 NS2. Look, for example, N is 4, that means 3D4 4S2. This is comparatively less stable than 3D5 4S1. Look, 4S1, it has lower energy than 3D. So what will happen, or what should be happened? Electron at first will fulfill 4s orbital by 2 electrons, then it will go to 3d orbital. But here, if one electron from 4d orbital comes to 3d for making 3d half-filled, then the electronic configuration will get more stability. And in the same way, the configuration N-1D10 NS1 becomes more stable than N-1D9 NS2. Here also, if one electron from 4s goes to 3d to make it fulfill, then this electronic configuration is comparatively more stable than this one. Therefore, the deviations are noticed in the electronic configuration of chromium, copper, molybdenum, silver, thorium, etc. Because in these elements, the last electron before fulfilling the lower energy shell, that means 4s or 5s, goes to higher energy shell to make them stable by half-filling or fulfilling. For example, for molybdenum, electron goes from 5s to 4d to make 4d half-filled, and the half-filled 4d orbital or full-filled any degenerate orbital will become more stable than other orbital. Now, look, the electronic configuration of chromium, copper, molybdenum and silver are shown here. Electronic configuration of chromium by following Outbound principle. Here, the last electron goes to 3d orbital. 4s, after fulfilling 4s by 2 electrons, there are 4 electrons left, and these 4 electrons have gone to 3d orbital. But look, here 3d4 4s2. 3d, if it gets 1 electron, then it will get half-filled condition. So here, another electronic configuration. Here 4s orbital gives 1 electron to 3d for making it half filled. Now from the general rule or Outbound principle, this electronic configuration should be correct. But chromium, it shows deviation for making the degenerate orbital half filled. So this electronic configuration is correct and this one is wrong. In the same way, if we see the electronic configuration of copper, then we will see here the last 9 electrons, they go to 3d orbital. But here also, if 4s orbital gives 1 electron to 3d, then this 3d orbital will get 10 electrons. That means fulfilled condition, and this electronic configuration is comparatively stable than this one. Though it is followed by Outbound principle, but this one is more stable. So the electronic configuration of copper, this one is correct and this electronic configuration is wrong. In the same way, molybdenum, here also if 1 electron from 5s orbital goes to 4d and makes it half filled 4d5, then it will get more stability, and this electronic configuration, though it is not followed by Outbound principle, but this one is correct and this one is wrong. In the same way, for silver, if 1 electron goes to 4d orbital and makes it 4d10 fulfilled, then it will get more stability and the electronic configuration of silver becomes this, and it is more stable than this. So it is correct electronic configuration and this one is wrong. So dear students, we have seen there are 4 electronic configuration which are not followed by Outbound principle. These are the deviation of Outbound principle, and why? To make stable by giving 1 electron to degenerate orbitals for making it half filled or fulfilled. Now another one, that is very small difference of energy between NF and N+1 d orbitals. This type of deviation is noticed in lanthanum series and lanthanide series and actinide series. In case of atoms of higher atomic number, the difference of energy between NF and N+1 d orbitals is very low. Therefore, sometimes one or more electrons may go from NF orbitals to N+1 d orbitals. The electronic configuration of lanthanum, actinium, thorium show this type of deviation. Look, if we write the electronic configuration of lanthanum by following Outbound principle from here, then we will see that the electronic configuration should be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f1. That means the 57th electron of lanthanum, it goes to 4f orbital. It will be 4f1. And if we arrange the electronic configuration, then it becomes like this. But there is one deviation for lanthanum. Here 4p and 5d, their energy difference is very less, and after the electron should fulfill at first 4f, then it should go to 5d. But for lanthanum, electron does not go to 4f orbital. There are very small difference in 4f and 5d, so electron goes to 5d orbital instead of 4f orbital. That means electron does not go to 4f. Look, there is no electron in 4f. Instead of 4f, electron goes to 5d orbital. But it is one deviation. Look here, the energy of 4f is less than 5d. So electron should go to 4f. But instead of going 4f, electron goes to 5d orbital for lanthanum. Here one thing is important, students, that is, in next chapter you will learn about this, that if the last electron of an atom goes to d orbital, then this atom is called d block element. If last electron of an atom goes to f orbital, then these atoms are called f block element. Here lanthanum is a element of lanthanide series, and you know the elements of lanthanide series and actinide series, they are f block element, but lanthanum is exception. Lanthanum is not the element of lanthanide series, and lanthanum is not the element of f block element. It is a element of d block element, because the last electron of lanthanum goes to 5d orbital. So it is a d block element. So here this is wrong electronic configuration. This one is also wrong, but this electronic configuration, it is correct. Here this electronic configuration, if we write it up to 5p6, that means fifth inert gas, helium, neon, argon, krypton, xenon, up to 5p6. This is the electronic configuration of xenon, and the electronic configuration can be written as xenon 5d1 6s2. The same type of deviation is noticed in actinium and thorium also. These two are also d block element instead of f block element. Though they are present in actinide series, but they are d block element because their last electron goes to d orbital. Look, actinium, its atomic number is 89. So the electronic configuration will be like this. Here 4f14, then 5d10, 6p6, 7s2 and 5f1. The last electron should go to 5f1. But here also the electron does not go to 5f orbital. It will go to 6d orbital, because the energy difference of 5f and 6d, it is very less. So if we arrange the electronic configuration of actinium, then it will become like this. Last electron goes to 5f1, but this is wrong electronic configuration. The correct one will be 6d1, because here the energy difference of these two orbitals is very less. So the electron goes to 6d orbital instead of going 5f orbital. So this is the correct electronic configuration, and these two are wrong. This electronic configuration also we can write up to 6p6. This is the sixth inert gas, that is radon, and then it is 61 7s2. In the same way, if we write the electronic configuration of thorium, the atomic number is 90. That means it will become 5f2. Here 89, it was 5f1 and it is 90, so there will be 5f2. But here also for thorium, the two electrons don't go to 5f orbital. It is wrong electronic configuration, and the correct electronic configuration is this one. Here the electron goes to 6d orbital. The both electrons, these two electrons, instead of going 5f orbital, they will go to 6d orbital for Why? Because the energy difference of 5F and 6D is very less. So my dear students, today up to this we have learned some electronic configurations which are not configured by general rule. They are the deviation from general rule. So you will remember this today. Up to this, here thorium, if you write by using inert gas, then it will be up to 6p6 radon, then 62 7s2. So goodbye everyone. Thanks to all. Goodbye.